Alright, well there's a catch here. The problem is that we can't actually see atoms, or we can't see electrons, so we don't actually know what they look like. And so what we need is a way to represent how electrons are arranged in atoms. The Bohr model is clearly not sufficient to do that. Well, let's use an analogy. We have here a little homemade radio, and it's got various parts. There's a battery, there's a bunch of wires here that makes an antenna. There's a transistor here and a transistor there, and resistors and capacitors and whatnot. If we look at that, we can see all the components, but we really don't see well how this thing is all connected up. To do that, we need some kind of a wiring diagram. That's usually referred to as a schematic diagram, and it represents all the components and how they're connected. Here we see the wiring diagram, or the schematic diagram, for this little radio. Now here's the catch. This schematic diagram doesn't actually look like the radio. Okay, here we see a wire over here. This is the antenna. That's this thing along the bottom here. Here's our battery that's next to it, but on the diagram it's up here someplace. Over here, this little widget up here on the metal is this tuning capacitor right here. What you barely can see right there is the volume control, and that's located right here. So the bottom line is that the schematic diagram shows how it's wired, but it isn't what the radio actually looks like. Well, since we can't actually see atoms and can't see the electrons, then what we need is a schematic diagram for an atom, and in particularly for the electrons and how they're arranged in all of the energy levels and sublevels. And so that's what we're going to use. We're going to have something called the electron energy diagram, which is a schematic diagram of an atom. And here you see what the energy diagram looks like. You'll notice that it's got lots of numbers and letters and little horizontal lines, and it all looks very confusing. A couple of things to remember are the number of electrons in an S, a P, a D, and an F sublevel. Okay, and the number of electrons in the major energy levels. And of course what we find then is that these little lines are going to represent places where we can put electrons. Now notice that we have one line here, and we can put 2 electrons in the 1s sublevel. So how many electrons are we going to put on this little line? The answer, of course, is 2. Here we can put 2. But look in the p sublevel. In the p sublevel we've got 6 electrons. So we need to account for 6 electrons. We've only got 3 lines. Clearly, just like these guys down here, there's going to be 2 electrons per line. So we have 2 here, 2 here, and 2 here. That's going to give me 6. That's going to take care of the 6 electrons that can be in the 2p sublevel. We've got 10 electrons in a D, so we have 1, 2, 3, 4, 5 lines, 2 electrons per line. And in the F sublevel, find an F sublevel up here, and sure enough we've got 7 lines which correspond to 14 electrons. Well, what do those lines represent? Each of those lines is something called an orbital. Notice in this case we have each of these lines that represents an orbital. Now an orbital is basically a region in space within an atom where 2 electrons can be located. Notice that the number represents the principal quantum number, and of course the S, P, D, and F represent the sublevels. Now what the dickens is an orbital? As we said, an orbital is a region in space where we can have 2 electrons. Now remember we said there was S, P, D, and F orbitals. An S orbital is basically spherical. When we have a p orbital, each p orbital, there are 3 of them, is actually dumbbell shaped. Where we get these orbitals is by a prediction based on the Schrödinger wave equation. Now at this stage of the game you don't really need to know about where the shapes of the orbitals come from, but they are predicted by an equation that generates a three-dimensional output, and that three-dimensional output takes on the shape of one of the orbitals, whether we're talking about an S or P or a D or whatever orbital. So in the case of the p orbitals, that space where the electron can be found has these two lobes, and this basically represents the location of two electrons. So we have two electrons on the x-axis, we have two electrons on the y-axis, two electrons on the z-axis. Together that gives us our 6 electrons. Now the d orbitals are even more complicated. Since electrons can behave both as waves or as particles, the fact that the Schrödinger wave equation is treating electrons as waves is what produces these lobes, much like the peaks and valleys in the sine wave when we represent waves on a two-dimensional graph. Again, don't worry too much about the shapes, but the fact that there are simply 5 orbitals, and each one of these shapes represents the location of 2 electrons within the d sublevel. Now, in our schematic diagram, we're going to represent an orbital much easier. It's simply going to be the line that we showed earlier. So the line represents the orbital, either an S, a P, or D, or F orbital. We're going to represent electrons with arrows, either an up arrow or a down arrow. If I have 1 electron in an orbital, we have a single up arrow. If I have 2 electrons in an orbital, we have an up arrow and a down arrow. Now the up arrow and the down arrow indicate something different about the 2 electrons in the orbital. Normally electrons with the same charge are going to repel each other. So why in the world would 2 electrons get close together in an orbital? The only way that can happen is if they have opposite spin. There's a property called spin, which basically has nothing to do with electrons spinning. Spin is actually a magnetic property. Each electron acts like a tiny little magnet. And so when electrons have opposite spin, one electron is basically oriented, say, with its north pole up, and the other electron is with its north pole down. That gives the north-south attraction at the top and the bottom of the pair of the electrons. It's a little more complicated than that, but that gets us in the right ballpark. You can never have 2 up arrows in an orbital. You can never have 2 down arrows in an orbital. The only thing we can have in an orbital is an up arrow and a down arrow, meaning the electrons have to have opposite spins. Now here we see the electron energy diagram for arsenic. Notice that we have orbitals that have electrons in them, orbitals that have 1 electron in them, orbitals out here that are empty. And we can basically have simply ignored those. We could have drawn our energy diagram up through the 4p and then quit. So we actually don't need to draw in extra orbitals. They just happen to have been left over. Notice that we have electrons which are paired. The interesting thing is what happens when we get out here to the 4p and we have 3 electrons, but notice that each electron is in its own orbital. Why is that? This is because of something called Hund's rule. Hund's rule basically says that orbitals at the same energy, in this case the 4p, each belong to one orbital. So it says that each electron goes into one orbital before the second electron is added to the orbital. The reason for that is that putting 2 electrons in 2 separate orbitals located 90 degrees apart is going to be lower in energy than putting 2 electrons in the same orbital. The other part of Hund's rule says that electrons in the singly occupied orbitals, meaning these guys right here, will all have the same spin. So this is why all the electrons are pointed up. So again, we have our electron energy diagram. We can break it down into its component parts. Starting with the 1s, Then the 2s and the 2p, notice how these go together. These constitute the 8 electrons in the second energy level. We keep on going up. We have the third energy level with its sp and d sublevels. So now we can hold up to 18 electrons. We go to the fourth energy level. Notice that the 4s is lower in energy than the 3d. So if we start with the bottom and we work our way up, we'll come to the 4s sublevel before we come to the 3d sublevel. You'll see later on that that's important. We've also added an f sublevel. This takes care of the 32 electrons we can have in the fourth energy level. Likewise, we've got the 5s through the 5f, the 6s through the 6d, 7s and 7p electrons. And that pretty much takes care of all the electrons that we can stick in an atom. Notice along the y-axis here we've got energy. So the 1s is at the lowest possible energy, 7p is at a high energy. Notice that when we're drawing the energy diagram, all the s's are in a vertical column. All the p's are in a vertical column. Ditto for the d's and the f's. So we see this little diagonal arrangement of the 2s and the 2p, the 3s, the 3p, and the 3d. The 4s all lie along a diagonal, ditto for the 5s. So that this is the convention that we use for representing the electrons within our little schematic diagram of the atom. Now the next thing we're going to look at, how we fill this energy diagram with electrons. It's a German word called Aufbau, which means building up. And the Aufbau principle refers to the building up of an atom, starting with the lowest energy and working our way up. And so as we add electrons to this energy diagram, what we're going to do is we start with the 1s, then go to the 2s, and then go to the 2p. We work our way up through the energy diagram in much that way. So we start with the 1s, then we go to 2s and 2p, then we go to 3s and 3p, 4s. Notice that the 4s fit between the 3p and the 3d, so next we go to the 3d. Then we come back to the 4p, the 5s, the 4d, the 5p, 6s. Then we jump to the 4f sublevel, back to the 5d, 6p, 7s, and into the 5f, the 6d, and the 7p. Now, this may look really complicated, but it's all actually very simple, because what it does is it follows our periodic table. Remember the S, P, D, and F regions of the periodic table? Well, look at an actual periodic table. When we are filling these, we start with the lowest energy, which in this case is at the top left-hand corner of the periodic table with hydrogen. So we do hydrogen, which is in the 1s. Notice the little 1s written right there. And helium, which is also in the 1s. So we go from hydrogen to helium. Then we go to the next energy level, which is the 2s. And then we go to the 2p. Then we repeat with the 3s and then the 3p. So it's just like reading a book, top to bottom, left to right. So from the 3p we go to the 4s. Notice that the 4s came after the 3p, and notice that the 4s becomes before the 3d. So now you see how that overlap worked. Okay, next we come to the 3d sublevel. Then we jump back into the 4p. We start the next energy level with the 5s. Then we go to the 4d, come back to the 5p. Start the next energy level with the 6s. But now something else happens. We jump from the 6s to the 4f. From the 4f sublevel we come back to the 5d. Then we go to the 6p. Repeat the whole process again with a 7s, 5f, and then the 6d, and at that point we've basically run out of electrons. So again, you see how this thing works. We start with a 1s, 2s, 2p, 3s, 3p, then the 4s, then the 3d. All this is doing is just following the periodic table. Just following the periodic table from left to right, top to bottom. And it matches the energy diagram as we go ever higher in energies.